Welcome back to Arxflix. Today, we're diving into a fascinating research paper titled Mixture of Depths: Dynamically Allocating Compute in Transformer-Based Language Models. This paper presents an innovative method to optimize the allocation of computational resources in transformers, enhancing both efficiency and performance. Here's an illustration of the Mixture of Depths transformer. The network dynamically decides which tokens to process through computationally expensive operations like self-attention and MLP, and which to route around, considerably reducing the compute required. Traditional transformers uniformly spread flops across all input tokens in a sequence. However, not all tokens require the same level of computation. The goal is to use a smaller total compute budget by allocating more resources to the tokens that need it most. The idea of conditional computation isn't entirely new. Pioneering works by Bengio and others laid the groundwork for dynamically deciding when and how much compute to use. But existing methods often result in dynamic computation graphs, making them incompatible with current hardware constraints that prefer static computation graphs. This paper addresses those challenges by introducing a static compute budget that remains fixed during training. The network then learns to dynamically allocate the available compute on a per-token, per-layer basis, optimizing the overall performance. Here are the routing schemes used in Mixture of Depths transformers. Tokens are routed either through computational paths involving self-attention and MLP, or through residual connections that save compute. The implementation involves setting a static compute budget, defining a per-block router emitting scalar weights for each token, and selecting the top tokens for compute-intensive operations. This ensures a predictable and context-sensitive compute allocation for each token. The equation illustrates how each token's future state is determined based on its router weight and current state. This routing system allows significant compute savings, as only the top tokens undergo expensive operations. The results are compelling. The Mixture of Depths transformers outperformed baseline models for the same computational budget. Notably, models using 12.5% capacity for self-attention and MLP computations showed optimal performance, indicating substantial capacity for reducing compute requirements. This technique isn't just about cutting down compute, it's about doing so intelligently. The models achieve comparable or better performance while requiring fewer flops per forward pass, and training times remain competitive. During isoflop analyses, Mixture of Depths transformers consistently performed well across different flop budgets. These models are not only faster to step, but outperform baselines with fewer forward pass flops. The researchers also evaluated the models in an autoregressive setting. Switching from non-causal routing during training to a causal predictor-based approach during sampling led to minimal performance degradation, ensuring efficiency gains carry over to practical applications. An exciting extension combines Mixture of Depths with the existing Mixture of Experts methodology, termed Mixture of Depths and Experts mode. This hybrid model leverages the strengths of both approaches, routing tokens among different types of computations, and showing compounded performance improvements. In summary, Mixture of Depths transformers open a new avenue for efficient and scalable language modeling. They highlight the importance of intelligent and dynamic compute allocation, paving the way for future research in optimizing large-scale models. Thanks for watching Arxflix. Don't forget to like, subscribe, and hit the bell icon for more deep dives into cutting-edge AI research. See you next time. Thanks a lot to Element for supporting Arxflix and providing this wonderful voice.